Okay, so this will be an overview of the BJX2 cores. On. Yep, checking. Yeah, this will be an overview of the BJX2 cores. Memory bus subsystem. This isn't directly visible to the code running on the core, but is currently related to its implementation on an FPGA. So, in the current form of the bus, the major signals are there's a data in port, which varies in size for the main L1 and L2 caches. It's either 128 or 256 bits, depending on the size of the cache line. And there's a data out port that's for what's being written back to memory. Then there's two address fields, at least on this form of the bus. In the L1 bus, it's 48 bits, and the L1 bus uses virtual addressing, whereas the L2 bus uses 32-bit physical addressing. 32 bits is sufficient on the FPGA because, well, the thing only has 128 megs of RAM at current, so don't need much more than that. There's two address fields. This allows for full duplex operation of the bus, namely simultaneously loading one cache line while writing another cache line back to the L2. And then there's an operation mode, which is what request is going on, and a status code for how that operation is going down. So yeah, the operation mode in its major form, uses two high order bits to indicate the type of command. So if they're all zeros, it basically means ready, which means the bus is, or means it's commanding the bus to not do anything or to get ready to accept another command. If the low 2-bit or the high 2 bits are cleared, but the low bits are something other than zeros, then it's basically a command. This would be things like cache flushes and TLB loading and similar. Then 2 bits, or then other bits here, can be used to encode load, stores, or swap operations. So a load would retrieve a cache line from memory, or read a value from the MMIO bus, and store would write a value or a cache line, and swap would exchange two cache lines. That's the full duplex operation described earlier. Both directions do operate at the same time, so they're basically the same, or part of the same request, as opposed to having a separate port for loading and storing cache lines. Low order bits and load, store, and swap operations, as can be noted, are this for a D word operation, so 32 bits, or both low bits set for a quad word operation. A lot of the other patterns are currently reserved. So for example, byte or 8-bit or 16-bit access isn't allowed over the MMIO bus, and similarly, what would be a 128-bit operation is in fact a cache line operation. This might change at some point in the future, but that's what it is for now. Response codes are kind of similar, but more limited. Basically, you have a ready request, so that the bus can accept a new request. Basically, this means that the bus is presumably idle. It could also be that it's, you're just not giving the bus a command, and it's telling the core that, it can begin initiating a new command. OK basically means that the prior request did its thing successfully. So, like, if your load happens, this is when the data would be visible on the data pins, or on the So, data is valid here. For stores, it basically means that whatever was storing has been now effectively written back, and the bus can be returned to a ready state. Hold basically is set when it's acknowledged that the command is being done, but the command isn't done yet. So this would be when the cache is accessing memory or similar. So it's like, in this case, it would generally be for an L2 miss, or an L2 miss. You might see this as it's accessing the RAM and transferring the cache lines back and forth. So yeah. Then there's fault, which basically can mean different things depending on context. Generally, it means the request has failed, or it can mean the request has failed, such as when doing a swap operation with settings that don't actually work, or it could indicate a fault or interrupt has occurred. These are similarly forwarded along this bus, but there's currently a separate mechanism for handling interrupts as well, but that may be phased out. So if with this status code set, the data in pin contains an exception code plus address. Address is in the high 48, or is in the upper 48 bits of a 64-bit value, and the exception code is in the low 16 bits, similar to what it would be for interrupts, but slightly different, or its use is slightly different in that values with the high bit cleared are also used, but these generally indicate request failed bus situations, as opposed to the high bit being set, which generally indicates a fault or interrupt. So, going back, if a swap is done, and if a swap is being done and a fault occurs, what that means is that the swap can't be done with these parameters, in which case the L1 cache will try again, but instead we'll use a store followed by a load. But most of the time the swap operation will succeed, so in general using swap is preferable for performance, even if in the worst case it needs to be broken down into several additional operations. Whether the use of swap or or store followed by load is better for performance seems to depend some on the workload. For example, memory copy operations seem to much prefer swap, whereas things like the dry stone benchmark currently seem to prefer the separate load and store operations, but guessing that might be due to cache pressure or access patterns or something. But, yeah. In the current bus, only a single request can happen at a given time. As noted, yeah. Handling requests takes up the entire bus. Need to wait for it to propagate and for the response to arrive. And this would be the OK. So first we send, like, for example, writing a cache line. This propagates the whole bus. Then so it gets to the destination and gets handled. And the OK comes back. At which point we send a ready request onto the bus, and then wait for the status code or for the OK value to switch back to ready. Once the OK value switches from OK to ready, that means that the bus is effectively torn down, and we can issue another command. This happens across all the bus levels for every request, which is currently a little bit of a a performance bottleneck, which I had been battling with recently. I may investigate other possibilities, such as switching from a bus design over to a ring network design. I'll get to that one later. That's all the slide magic. So here we can see the general organization of the bus. So you'd have the L1 instruction cache and L1 data cache sharing a common bus interface with the fields as described previously. These are part of the L1A module, which also contains an MMU. Pretty much any of the requests we'll hear in here would be produced in virtual address or in the virtual address space, and then they hit the MMU and get transformed into physical addresses, which are what the rest of this uses. For the L1 data cache, when the request happens, it will also send some information from the MMU back to the data cache, such as, for example, the bits needed to rebuild the physical address. The reason that these are needed is basically because if an interrupt occurs, you need to be able to write the cache lines back out to memory and similar, and generally the interrupts are happening without the MMU being used because, well, you can't handle like a TLB miss inside of a TLB miss. So to simplify matters, these operations or interrupts and similar occur only in the physical or only with physical addressing rather than virtual addressing. Which basically means that the data cache also needs to be able to speak in terms of physical addresses as well. And, well, presumably your virtual addresses and physical addresses don't overlap because that's, another mess. So yeah, but other than that, it also would forward some information such as like page access flags and other stuff to the data cache, so it can be all like you're trying to write to something that's read only and generate a fault and similar. in effect, like the data or the cache or the L1 caches can't raise interrupts directly, but instead would be all like, oh, here's an interrupt, and send a command out to the bus, which would then be seen as, oh, raise an interrupt, and send that back into the CPU core. Similarly, like, well, an interrupt can also be routed back or to another core and similar. So in this case, it would basically be all like go from here to here, then out to the Y joiner, and then to the L2A stage. In which case, this would be a cache command, which would then transform back into into a fault signal or similar, and then go back up to the Y joiner, which would basically be like, oh, I see an interrupt, and which core does it go to, and then it will route it as appropriate, and it will be able to send interrupts between cores. Yeah, as noted, once it gets here, like this will more or less multiplex these two and also translate it to a physical address. The Y joiner will effectively multiplex between the two cores, basically only allowing one of them to send a request through at any given time. So earlier on, it would the bus would automatically send back a hold signal if it tried to access the bus, and the bus is already busy, but I realized that caused some ambiguity, because the bus could go from basically ready to a hold state, then back to a ready state, and in the process it could have caused the L1 caches to think that the request actually began when it hadn't began yet. So instead, what will happen is the bus will just hang out at a ready state, even if it's not accepting the command right then. So the cache will just keep waiting for the bus to do its thing until it does its thing. So yeah, but once the Y joiner multiplexes the two cores, and it only lets one of them, or lets the request from one of them out, it'll go over to the L2A, which is the main part of the L2 bus. L2 bus would basically multiplex that between, well, either the L2 data cache for anything that maps to a RAM address into the boot ROM or boot SRAM or similar, for things like for the relevant address ranges, or if it's an MMIO request, it'll be sent out to the MMIO bus, which also is a big multiplexer. This would basically contain things like the display interface, or SD cards, SPI interface, or keyboard interface, or so forth. Yeah. So yeah, L1 bus connects the L1 instruction and data caches to a common interface, routes the bus through the TLB, and yeah, the TLB functions as a bridge to the external L2 bus, and so it has data in, data out, which are full cache line width, then the two addresses, which are 48-bit virtual in the L1 bus, and also the OPM and OK signals. So the TLB maps the 48-bit addresses to the 32-bit addresses, as described previously, and yeah, currently it functions as the bridge to the L2 bus. Yeah, as noted, the L1A block actually, in the current implementation, actually contains the caches, and also implements the L bus. So they all function as a single big module as far as seen externally. This basically works for the moment. And the Y joiner, yeah, it's mentioned already, joins together multiple cores and mostly just forwards requests. Actually, going back to the picture, that this was a source of latency as well recently, because this part would happen, only in, or this part would exist completely within the partial simulation, but not within the full simulation. So from here, data could be moved pretty fast to and from the simulation, because pretty much all of this stuff out here would have been handled by the test bench in the partial simulation, whereas in the full simulation and in the CPU core, this is all going on in Verilog as well. But because each of these stages here added basically a few clock cycles, and because of the way the bus signal propagation worked, it actually turned out to be a pretty serious bottleneck. So if the whole process takes 24 or so clock cycles for every operation, or for every request, that can pretty quickly hinder performance. Yeah, I talked about these already. So yeah, the L2A module effectively glues together the secondary buses. Namely, this is the L2 bus. Connects to the L2 cache, boot ROM, and also the MMIO bus. And it serves to separate out requests between memory and MMIO. These are tagged slightly differently, so it can use the slightly different OPM value to determine which bus it goes to. It also handles a few cache commands in similar as well. So partly that's where that happens, but some of those signals are also used for signaling to other parts of the memory subsystem. L2 bus is similar to the L1 bus, except for using physical addresses. So similarly, cache line sized data fields and 32-bit physical addresses, still using OPM and OK signaling. But this isn't true with the MMIO bus, which I'll describe later. L2 data cache, it sits between the L2 bus and RAM. The RAM module uses the same basic interface as the L2 bus, so and it's actually possible to entirely omit the L2 cache and just sort of plug the RAM directly into the L2 bus. There's a tiny bit of additional logic involved in doing this, but more or less it's pretty close to a straight plug the RAM into the bus situation. This has some different effects for performance. Skipping the L2 cache, makes mem copies slightly faster if it's a RAM to RAM copy, but as noted, we have none of the benefits of the L2 cache in this case, and generally things are slower if the L2 is disabled for reasons that probably aren't too hard to guess. But, so things like Doom and Sim are kind of really like the caches to be present, even if, like, the actual raw, like, RAM to RAM mem copy speed is slightly slower. So yeah, mostly holds cache lines to reduce the number of accesses to external RAM, and yeah, the DDR, the DDR interface doesn't actually perform any caching on its own, so its job is mostly pretty directly to read and write, or to load and store cache lines from the external RAM module. And the L2 data cache also implements full duplex / swap operations. Yeah, so it's, loads cache line while simultaneously storing another, and may fault in some situations, in which case it has to fall back to half duplex operations. Swap doesn't actually work if the L2 isn't used. So, for example, bypassing the L2 will only work with half duplex or discrete load and store operations. Yeah. So it's, differences there. But, boot ROM and SRAM use the same interface as the L2 memory bus. Yeah, I guess that would make sense because they are on the L2 memory bus, but yeah, it's a little bit of an oversight probably. Yeah. Yeah, so there's currently 32K of boot ROM, which is mapped between the 0 address, or basically in the low 32K of address space. And then there's potentially, if needed at some point, I could give another 16K or so to the boot ROM as well, which I might actually end up doing at some point, given I've already used up most of the existing 32K space. Currently, like, the boot SRAM is also 8K, but could be expanded to 16K if needed. But it's not needed yet, and also block RAM isn't free, so yeah. The purpose of the boot ROM is mostly to load the bootload.sys file from the SD card. This is basically what would function as the kernel image. At present, this is stored as basically an LZ compressed PECOF binary, so, or the PEL format, or PEL, or whatever one wants to call it. But yeah, so the boot ROM both loads the file from the FAT file system and also decompresses it into a PECOF image in memory, and then it sort of runs it, and that's how it boots. The boot SRAM is used for the bootloader's data and stack areas, and post-boot it's also used for an interrupt stack. Well, partly because there needs to be some use for it. conceivably, conceivably I could have skipped having a dedicated SRAM for the bootloader and similar, but kind of having it existing kind of makes sense. And the ancestor architectures it was derived from also had a dedicated RAM region mostly for the bootloader and ROM and similar to use. So it's partly where that came from. So yeah, the MMIO bus. This uses a slightly narrower 64-bit data path, and load stores pass through the data bus more directly. Namely, it doesn't actually use cache lines when accessing MMIO, but will actually directly load or store discrete values. So they're basically just forwarded to the appropriate bus and such. It's possible that the CPU core could have used an entirely separate mechanism rather than MMIO, such as it could have for example used IO ports like on x86, but MMIO does effectively work and doesn't require using separate instructions for the two different types of IO. Effectively does exist in a different address space from the normal memory, namely within the high 256 megs of the first 4 gigs. This is a special address range, so it actually will be handled specially by the TLB and similar as well. Maybe. Yeah, actually I think if I remember correctly, it just ignores MMIO requests in general, so it's not about the address, but rather that it's an MMIO request. But in any case, yeah. But yeah, the cache will, or the L1 data cache will see that this address range is used and do an MMIO request rather than a RAM request. And as noted, the MMIO bus currently uses a 28-bit addressing scheme, which is are probably plenty sufficient now because there's not that much space that's needed by peripheral hardware. And as can be noted, it's half duplex and only a single address field is used for accessing the MMIO bus. So loads and stores, but no swap operations or anything like that. And also no cache lines, because for reasons. Possibly 128-bit MMIO could make sense as an optimization, but currently that's not done, and it would add cost and similar as well, so probably not worth it at the moment. The other question is, what if instead of using a big bus we used a ring network? So that's what this diagram depicts. It's like instead of the messages happening one at a time and locking or taking up the whole bus, instead you'd have a sequence or a ring of messages being passed in, well, a ring. So they'd be spinning around if there's no request and you want to send a request, you can just be like stick it in the ring and send it out to the next item, and then it'll spin around until it gets where it's going. When it gets, if it's out to, so say L1 here wants to access memory, it'll wait till it's an empty spot, and then it'll send out its request, which will go over to the data cache, which won't do anything with it. It'll just forward it out the other side. It'll be all ping, forward it out to here. Then the MMU will be all like, oh, this thing goes to RAM, translate its address, and then might, say pass it over to the next MMU, which would be, oh, like, yeah, I can't do anything with this. It just forwards it on to the MMIO, which would be all like, nope, or all like, nope, doesn't go here, and pass it on. Then when it gets here, it'll be all like, oh yeah, I know what to do with it. Then it'll fetch the cache line and then pass the result back up here, which would be all like, okay, it's a response. Then, pass the response back to the L1I cache, in which case it'll be all like, yep, got it, got data now. And similar for the other cores and so on. I just left this part as is because that was least effort, but it's possible it might make sense to say move the display module up to the L2 ring for improved performance. But that's possibly its own topic, maybe. But yeah, I'm not sure if I will do this yet, and it would actually be probably a pretty big chunk of effort, because it would require more or less redesigning the entire bus, but it could possibly offer higher performance. So in ring network, it's a possible alternative approach. So L1 and L2 buses could be replaced by rings, as noted, and messages spin along the ring until they get to where they're going. And multiple requests could happen at the same time. This would be the main possible advantage of going over to a ring. Because, well, unlike the current bus where only a single request can happen at any given time over the entire bus. However, the latency for any single request could be higher, namely because, well, as noted, it has to bounce around the ring. So, say the L1 request situation, if we assume here to here takes one cycle and here to here takes one cycle, then we have additional 3 cycles to translate the request. So this would be 5 cycles, then 6 cycles, and 7 cycles, then 8 cycles, then 9 cycles by the time it reaches here. Then assume this takes 3 more cycles, so 14 cycles here, and 15, and 16. Yeah, so this would take about 16 cycles of request latency for the message to get all the way around, which would be worse than the current 9 cycles. Like after I optimized it, it was 24 cycles before that, but I optimized it some and got it down to 9 cycles of latency. But yeah, so the actual latency would be higher for any given request. However, the main advantage would be you could have multiple requests traveling the bus at the same time. So say if a data cache miss happens, then it could, just sort of throw both of the cache lines that it's storing back out onto the bus and the 2 requests out into the bus, and then that as they're traveling along, it would, well, take like, say, like, you know, another 17 cycles or so to get back, but the requests would arrive one after another, so the actual total time spent waiting for the data to get written out and come back might be less. Yeah, unlike the current bus, there wouldn't be an actual teardown stage, so that's part of what gives it a fighting chance. Yeah, both requests and responses would be, they'd be ring messages. That's a little bit confusing, but yeah. But like both, like, you know, stages would be handled like in ring, so or via messages in the ring, so there's no actual separate teardown stage necessary. And each node is connected to the next and previous messages, or to the next and previous nodes, and connected in the ring. As noted. If we look at here again, the previous one would be the data cache, and then the next one would be the next MMU, and so forth. They just sort of accept messages in one side and send them out the other. So possible messaging structure for the ring network. You would have data in and out fields for the data for each message. This could be, for example, an entire cache line, but possibly it could also be smaller. That would be if you wanted to send data as multiple pieces, but that would be worse for throughput, so it's a trade-off. Then you'd have an address field for the message. Since each operation is half duplex, or implicitly like half of the duplex, maybe. Well, the bus itself would be full duplex by definition, but given each message only handles half of the request, it would only need one single address. And you'd have the OPNM and OK probably combined into a single 8-bit field as opposed to 2 separate fields. This would be because they're both traveling in the same direction in this case, and because they're effectively conjoined. Then you would have a source ID to indicate where the request originated and where the response will be routed to. The operations needed for each node would be fairly simple. Namely, either removes a message from the bus, adds a message to the ring, or passes a message along unchanged. So if a node is either busy or if it's busy or doesn't understand the message or whatever, it'll just keep forwarding the messages along until either it can handle it or like something that it recognizes shows up. Nodes will simply forward messages which don't belong to them, as noted. So basically, there'd be a combined OPM and OK value, which would probably use the high 2 bits as a as an OK or OK, yeah, as an OK field. So for a newly created request, these would be set to 0, which basically means to route based on the address to wherever it's going. So this would be moving away from the L1 caches. If it's set to OK or fail, then it would basically be routed back towards wherever it came from. So once a cache line is written back, it will basically send a message back to the cache that indicates that the cache line's been written back, or if it's a load requesting a cache line, then the OK response would carry the data back to the cache that sent it out, or sent out the request, and then it has its data. Or it could fail, which would be routed in roughly the same way, but would contain the failure code instead. Or it could be an interrupt, which would be a separate mechanism this time, or partly a separate code this time, and would be route based on the exception code. So, this is based under the assumption that the fault or interrupt isn't actually tied to a specific request, so it doesn't make sense to try to route it back to where it came from, but rather just route it to which party it would actually make sense for it to handle it. So the operation would be similar to before, except it could possibly give a little bit more encoding space to commands. Say, in this case, in this case it would basically give about 5 bits for commands, so 32 possible commands, and load and store ops would also be present. This is partly because with the current scheme there's not really enough encoding space for commands, so it gets a little bit messy. But in this case I could give a little bit more encoding space to commands. Similarly, the lower bits could be expanded to 4 bits, which would be relevant for commands, but for loads and stores, there's kind of not really a shortage, so doesn't make that much sense for those, but either way, 3 bits. Yeah, so it's probably a similar pattern before too, where MMIO ops would have these 2 patterns, whereas cache lines could have this pattern. Yeah, and that's basically the end of it. Yep, diagram magic. So, yeah, but yeah, as for why I'd possibly want to connect the display up to the ring bus rather than leaving it on the MMIO, the reason it turns out display or writing to the display is actually a relatively high bandwidth operation, so it almost makes more sense to have it on a slightly faster bus and to be able to write larger chunks of data to the display interface. Say, could make sense to be able to transfer 128 bits of time to the display memory as to the current limitation, or current interface, where it's actually limited to 64 bits. Also, it's possible that putting the display on the ring bus could make sense, because as is the display implements its frame buffer and block RAM and similar, whereas if it were put onto the bus here, then what it could have, or also have the option of doing, would be to say to map the display over to RAM or map the frame buffer over to RAM or similar, and with a ring buffer interface, the plumbing would actually be basically the same, so it would not have to do anything really that much extra to be able to access RAM, whereas in the current interface there's actually no good way for MMIO devices to be able to send requests for RAM, and even if they could, they'd be kind of slow and awkward and similar. So it is still a little bit of an open question as to whether or not the RAM interface would be actually fast enough to be able to handle non-trivial display modes. But that's probably its own issue. In any case, there would probably be enough bandwidth to handle the current 320 by 200 modes and similar, but say something like 640 by 480 at 16 bits per pixel would be putting pretty big strain on the RAM interface, so probably using a good chunk of the total memory bandwidth, which would be not ideal. But it would allow it to be done at all, which is different than the current situation where if you want 640 by 400, it either has to be 16 color or color cell. Yeah, the current display module does support those modes in color cell and in 16 color, but yeah. Then the question or thought is, well, what would I do with all that extra freed up block RAM, that I wouldn't be using for the VRAM anymore, which could probably be distributed among the L2 cache and maybe also make the L1 caches bigger as well. So say I could afford what would be by current standards a relatively monstrous 256K or so of L2 cache as opposed to the current 128K, but yeah, it's a possible trade-off, but might be an issue though if it comes at the cost of bogging down memory bandwidth by trying to run the display off of the external RAM. And it's possibly one of those, I might cross that bridge when I get to it situations. I don't actually know if I'll do anything with the whole ring buffer idea yet, but it is one possibility. Trying to think of if there's anything else I really need to say on this stuff. Yeah, I'm probably going to call it done.